Now, in this lecture, we'll find out the green area using three different methods. In the drawing, we have a quarter circle. Inside the quarter circle, we have a small circle. We know that line segment CD equals to 8 units, angle ACD equals to 90 degrees, and our mission is to find out the value of the green area. So we'll start with the first method, and we will define the center of the small circle as point J. We will define the point of tendency CD with the small circle as point E. We define the point of tendency of tangent OB with this small circle as point F. We will join points J and F together by a straight line. Point J is the center of the small circle. Point F is the point of the circle itself. Therefore, JF is the radius of this circle, of the small circle, that we define as R. So JF equals to R. And here we have the radius JF that is drawn to the point of tendency. Therefore, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to each point of tendency. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we'll join points J and E together by a straight line. Point J is the center of the circle, point E is the point of the circle itself, therefore JE is the radius of the circle that is equal to R. And according to rule number 1, the radius JE that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. We know that this is a quarter circle. In any quarter circle, this is the center of the quarter circle. Point O is the center of the circle, quarter circle, and this angle is equal to 90 degrees. Here, AO is the radius of the quarter circle, so we define the radius of the quarter circle as capital R, therefore AO equals to capital R. So AO is a radius of the quarter circle, it is absolutely a straight line. And we have rule number 3 that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line AO at point C, which angles we have? Here, this angle equals 90 degrees, therefore the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be also equal to 90 degrees. Okay? So here, from the center of the small circle, that is to say from point J, we draw perpendicular on CO. So here, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So inside quadrilateral TJOF, inside this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Plus the size of the fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, in order to complete the sum of the angles in quadrilateral TJOF to 360 degrees, this angle must be equal to 90 degrees. Likewise, if you focus on quadrilateral CETJ, this quadrilateral, inside this quadrilateral we have 1, 2, 3 right angles, and according to the same rule, the fourth angle must be also equal to 90 degrees. So here, angle EJF, this angle is equal to 90 degrees plus 90 degrees is 180 degrees. So here you can write down that angle EJF is equal to 180 degrees. And because of the fact that this angle EJF equals to 180 degrees, it means that EJF is a straight line. EJF is a straight line, and if AJF is a straight line, AF is also a straight line. EF is also a straight line. Okay, here EF is a straight line. Okay, you can write here that EF is a straight line. EF is a straight line. So if EF is a straight line, here EF is a straight line, it means that quadrilateral CEOF, quadrilateral CEOF this quadrilateral CEOF has 4 right angles, and therefore quadrilateral CEOF is a rectangle. Quadrilateral CEOF is a rectangle because it has 4 right angles. Okay. Quadrilateral CEOF is a rectangle. Here, this quadrilateral COEF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, EF equals to CO. EF equals to CO. But what is the value of EF? EF equals to R plus R, that is 2R. EF equals to 2R. And from this equation, 2R equals to EF equals to CO. We will derive that CO is also equals to 2R. CO equals to 2R. Here we can write down that CO equals to 2R. CO equals to 2R. Okay. In the next step, we will join points O and D together by a straight line. Point O is the center of the quarter circle, as I already explained. Point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to R according to our definition. So in the next step, we will implement the Pythagoras theorem on the right green triangle, triangle COD. On the right green triangle, triangle COD. By PT is the abbreviation from Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here, the hypotenuse of the right triangle, triangle COD, is OD. Therefore, the square of the hypotenuse is OD square. That is equal to the sum of the squares of the perpendiculars, that is to say it must be equal to CO square plus OB square plus CD square. Here, the right triangle COD is plus CD square. Repeat again. In the right green triangle, triangle COD, according to the Pythagoras theorem, OD square equals to CD, OD square equals to CO square plus CD square. So OD square. OD is the radius of the quarter circle that is equal to capital R, therefore OD square is capital R square, that is equal to CO square. We already found out that CO equals to 2R, 2 small r, therefore CO square equals to 2R square plus CD square. CD equals to 8, therefore CD square is 8 squared, that is 64. So in conclusion, according to equation number 1, we found out that R square equals to capital R square equals to 2R square plus 64. So here R square equals to 2R square is 4R square plus 64. Here we subtract 4R square from this equation, equation number 1, and we get that according to equation number 1, R square minus 4R square equals to 64. Okay, we actually found out that R square minus 4R square equals to 64 according to this equation, equation number 1. Okay. But what is the value of the green area? Although it is very easy to see that the value of the green area will be equal to the area of the quarter circle minus the area of the small circle. So I write it down. The area that we are looking for is the green area, and the green area is equal to the area of the quarter circle minus the area of the small circle. Okay, I repeat again. The green area equals to the area of the quarter circle minus the area of the small circle. So the area of the quarter circle equals of course to the area of the circle over 4, that is to say it will be equal to pi r square, r is capital R, over 4 minus the area of the circle, of the small circle, that is equal to pi r square, and here r is the small r. So here we take pi over 4 as a common factor of those two expressions. So here pi over 4 is a common factor. So what is left from pi r square over 4 after we took from it pi over 4 is a common factor? What is left is actually r square. And here we have pi r square. We took pi over 4 as a common factor, therefore here we will have 4 r square because of the fact that 4r square times pi over 4 equals to exactly to pi r square. So I found out that the green area equals to pi over 4 times r square minus 4r square. But this expression, pi r square minus 4r square, we already found out that r square minus 4r square equals to 64. That is to say, we can substitute r square minus 4r square by 64. Well, according to equation number 1, this expression equals to 64. So we do it now, we get that pi over 4, and this expression equals to 64. So we got that the green area equals to 64 pi over 4. 64 over 4 is 16. So this expression in total equals to 16 pi. 16 pi is about 50.265 square units. Okay, so we actually found out that the size of the green area, the value of the green area, equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first method. In the next step, I'll present to you the second method to find out the value of the green area. Okay, I will not repeat on the same things that we did in the first method. Here, this is the center of the circle, the small circle. This is the radius, this is also the radius of the small circle, and we have already found out that CD equals to 2R, so I'll not repeat on it. We proved that CD equals to CO equals to 2R. And here AO is the radius of the quarter circle. Therefore, AC will be equal to AO minus CO. Again, AC equals to AO minus CO. That is to say, it equals to AO, that is R, minus CO, that is 2R. Okay. So, in the next step, we will do a construction. We will complete the quarter circle to a circle. Okay, we completed this quarter circle to a circle. We will extend line segment CD by a straight line until it intersects with the circle, and we'll define the intersection point of the extended line segment CD and the circle as point L. In the next step, we'll extend the radius AO until it intersects with the circle. We define the intersection point of the extended radius AO and the circle SM. And here we will join points O and L together by a straight line. Point O is the center of the circle, point L is the point of the circle itself, therefore OL is the radius of the circle that is equal to capital R. We join points O and D together by a straight line. Again, point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that is equal to capital R. AO is the radius of the circle, therefore it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, this point C, here the sum of the angles must be equal to 180 degrees. So this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees, this angle must be equal to 90 degrees. Likewise, we'll focus, we know that we extended the straight line CD by a straight line, therefore the result must be a straight line. So here LD is a straight line. So if we focus on the lower side of the straight line LD at point C, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line LD at point C? We have this angle that is equal to 90 degrees. Therefore the missing angle must be also equal to 90 degrees in order to complete the sum of the angles in the lower side of the straight line LD at point C to 180 degrees. This angle must be also equal to 90 degrees. According to rule number 3. Okay, so we have here triangle LCO, and we have triangle that is a right triangle, and we have also triangle COD that is also a right triangle. We'll actually prove that those two right triangles can go into each other. So I write it down. We'll prove that the right triangle LCO is congruent to the right triangle COD, this right triangle. So why those two right triangles can go into each other? First of all, side CO is a common side that belongs to both triangles, so CO equals to itself. CO equals to CO is a common side that belongs to both triangles. Repeat again. Side CO equals to itself is a common side that belongs to both triangles. In addition, LO equals to OD, they are both the radii of the big circle, therefore they are equal to each other. LO equals to OD equals to capital R. LO equals to OD equals to capital R, they are both the radii of the circle, therefore they are equal to each other. So actually, we proved the triangle LCO congruent to the right triangle, triangle COD. I will explain why it is enough to prove that the two right triangles congruent to each other. We have one perpendicular and the hypotenuse in this right triangle is equal to the perpendicular and the hypotenuse on triangle LOC. Why it is enough to prove that the two right triangles congruent to each other. For example, if we have this triangle, the right triangle, triangle ABC, this is the right triangle, triangle ABC, this angle equals to 90 degrees. And we have also the right triangle, triangle DEF. This angle equals to 90 degrees. On those two right triangles, the hypotenuse is equal to 5 units, so the hypotenuse of those two right triangles are equal to each other, and we have one perpendicular that is also equal in those two right triangles. Okay, so if we have the hypotenuse and one perpendicular that congruent in two right triangles, then the third angle, the third side must be also congruent. Why? Because according to the Pythagoras theorem by PT, we get that the missing angle, the missing side BC, what is the value of side BC according to the Pythagoras theorem? It will be equal to 5 square minus 3 square. The square root of 5 square is 25, minus 3 square is 9, and 25 minus 9 is 16, the square root of 16 is 4. And also, this side EF also will be equal to 5 square minus 3 square, the square root of 5 square minus 3 square. So, here in this example, I showed you that if we have two right triangles that the hypotenuse and one perpendicular congruent to each other, then the third side must be also congruent. Here, the missing side BC is equal here to 4 units, and the missing side EF is also equal to 4 units. So, and we proved that in those two right triangles, the hypotenuse is equal, they are both equal to R, therefore they are equal to each other, and one perpendicular CO is a common side, therefore the third side LC, must be also congruent to side CD according to what I showed you here, because the third side must be equal in those two right triangles according to the Pythagoras theorem. Okay, here, those two sides are equal to 4 units. So therefore we actually proved that the right triangle LCO can go into the right triangle COD according to the rule that I showed you, that if one hypotenuse if the perpendicular and the hypotenuse in one triangle can go into the other right triangle, then those two triangles can go into each other. So from the fact that triangle LCO can go into the right triangle, triangle COD, we will derive that CD equals to LC. CD equals to LC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say CD and LC, must be also equal to each other. But it is given as the equation that CD equals to 8 units, so we can write here that CD equals to 8 units, and for this equation 8 equals to CD equals to LC, we will derive that LC is also equals to 8 units. Here LC equals to 8 units. Okay. So we found out that LC equals to 8 units. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the big circle that is equal to capital R. Okay? In the next step, I'll present to you rule number 11, and we'll implement rule number 11 in our drawing. According to rule number 11, if we have chord AB that intersects with chord CD at point O, so if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, so now we will implement rule number 11 in our drawing. In our drawing, we have chord AM. This chord AM intersects with chord LD. Chord AM intersects with chord LD at point C. Repeat again. Chord AM intersects with chord LD at point C. The intersection point is at point C. That is to say, we can implement here rule number 11, and according to rule number 11, we will get that LC times CD is equal to AC times CM. AC times CM. So actually, this equation is the implementation of rule number 11 in our drawing. LC times CD equals to AC times CM. Okay. So here LC equals to 8 units. CD is also equals to 8 units. And it is equal to AC. AC equals to R minus capital R minus 2R times Cm. What is the value of Cm? It is very easy to see from the drawing that Cm equals to capital R plus 2R. Capital R plus 2R. So in conclusion, we found out that according to equation rule number 11, 8 times 8 equals to R minus 2R times R plus 2R. 8 times 8 is 64, and it is equal to R minus 2R times R plus 2R, according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. Here A equals to capital R and B equals to 2R. Therefore A squared is R squared, capital R squared, minus B squared. B squared is 2R squared, that is 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. Okay, repeat again, 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Write it down again. The area of the quarter circle on the area of the green shape equals to the area of the quarter circle minus the area of the small circle. That is to say, the area of the quarter circle is equal to the area of the circle over 4. That is to say, it is equal to the area of the circle that is pi capital R squared over 4 minus the area of the small circle that is equal to pi R squared, and R is the small r. Okay, so here we take pi over 4 as a common factor. So here pi over 4 is a common factor. What is left from pi R squared over 4 after we took away pi over 4 is a common factor? What is left is actually R, capital R squared minus here we have pi R squared, so here we have to multiply it by 4 R squared because of the fact that 4 R squared times pi over 4 will equal exactly to pi R squared. So we found out that the area of the green shape equals to pi over 4 times R squared minus 4R squared. But this expression, capital R squared minus 4R squared, we have already found out that capital R squared minus 4R squared equals to 64. Therefore we substitute capital R squared minus 4R squared by 64. And we get that pi over 4, and this expression equals to 64. 64 over 4 is 16, so this expression in total equals to 16 pi, or in terms of numbers it is equal to 50.265 square units. So we finished the second method. In the next step I present to you the third method. So this is the center of the small circle. This is the radius. This is also the radius. We have already found out that CO equals to 2R, so I'll not repeat on it. AO, this is the center of this quarter circle. So AO equals to capital R, it is the radius of the quarter circle. I'll not repeat on it that AC equals to capital R minus 2R. We'll complete the quarter circle to a semicircle. Here. We'll define the touching point we'll extend here the radius AO. We'll define here the touching point of the extended radius AO, and the semicircle is point M. Point O is the center of the circle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle that is equal to R. We actually extended here the radius AO by straight line. AO is the radius is a straight line, and we extended the straight line by straight line, therefore the result AM, when you extend a straight line by straight line, the result must be a straight line. So AM, that is equal to 2R, is a straight line. So we have in this semicircle a straight line that is equal to 2R. Therefore, it must be the diameter of the quarter circle. You can see it as a chord AM that is equal to 2R. Chord AM equals to 2R, and it passes from the center of the semicircle, that is to say from point O. Therefore OM must be the diameter of the therefore AM must be the diameter of this semicircle. So I write it down. AM is the diameter of the semicircle. Again, because of the fact that chord AM passes through the center of the semicircle, that is to say from point O, and it is equal to R, any chord that passes through the center of the circle and it is equal to 2R must be the diameter of the semicircle, therefore AM is the diameter of the semicircle. Okay, so here we know that AO is the radius of the semicircle. Therefore, it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at this side of the straight line AO at point C? We have this angle that is equal to 90 degrees. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be also equal to 90 degrees. Okay, so in the next step we'll join points D and M together by a straight line. We'll join points A and D together by a straight line. By joining those two points together and points A and D by a straight line, we created here peripheral angle ADM. This is peripheral angle ADM, and we have already found out that AM is the diameter of the semicircle. So we have peripheral angle ADM that rests on the diameter of the circle. So here we have rule number 5. According to rule number 5, here, according to rule number 5, any peripheral angle that rests on the diameter of a circle must be equal to 90 degrees. And again, any peripheral angle that rests on the diameter of a circle must be equal to 90 degrees. Here we have peripheral angle AMB that rests on AB, that is the diameter of the circle. Therefore, peripheral angle AMB equals to 90 degrees. Okay, we can implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle ADM that rests on AM, that is the diameter of the circle. Therefore, peripheral angle ADM must be equal to 90 degrees according to rule number 5. This angle equals to 90 degrees. Okay, we define angle AMD as alpha. We define angle MAD as beta. We'll focus on the right triangle, triangle ADM. On the right triangle, triangle ADM, this right triangle, this is a right angle, it is equal to 90 degrees. So if this angle equals to 90 degrees, it means the other two angles here must be also equal to 90 degrees, because 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any right triangle, in any triangle. So alpha plus beta must be equal to 90 degrees. Alpha plus beta must be equal to 90 degrees. Alpha plus beta must be equal to 90 degrees. So here, if we subtract beta from this equation, we get that alpha equals to 90 degrees minus beta. And if we subtract alpha from this equation, we get that beta equals to 90 degrees minus alpha. Okay, so we'll focus on the right triangle, triangle MCD. In this right triangle, this angle equals to alpha. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. It is the sum of the angles in a triangle. So we found out that this angle, the missing angle, must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta. That is to say, this angle that is equal to 90 degrees minus beta, 90 degrees minus alpha, this angle that is equal to 90 degrees minus alpha equals to beta. Likewise, we'll focus on the right triangle, triangle ACD. On the right triangle, triangle ACD, this angle equals to 90 degrees, this angle equals to beta. Therefore, the missing angle here must be equal to 90 degrees minus beta. But here we have already found out that 90 degrees minus beta equals to alpha. So here, this angle that is equal to 90 degrees minus beta, it is equal to alpha. So in the next step, we'll prove that the green right triangle ACD, this right green triangle, is similar to the green right to the right triangle, triangle DCM. So I write it down. We'll prove that the right triangle, the right green triangle, triangle ACD, this right green triangle, is similar to the right triangle, triangle CDM. So, why those two right triangles are similar to each other? First of all, this angle CDA, in the green right triangle, angle CDA is equal to this angle that is actually angle CMD. And both those two angles, they are equal to alpha. Yeah, both those two angles are equal to alpha. In addition, angle CAD, this angle, is equal to this angle that is actually angle CDM. Both those two angles, they are equal to beta, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. That is to say, angle ACD, this angle ACD, is equal to this angle, that is actually angle MCD. Repeat again. Angle ACD equals to angle MCD. They are both equal to 90 degrees, therefore they are equal to each other. Those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So we actually proved that the right green triangle, triangle ACD, is similar to the right green triangle, triangle CDM, according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that AC in the green right angle, AC over CD in this right angle, CD, equals to CD in the green right angle over CM. I'll repeat again. From the fact that the two right angles are similar to each other, we will derive that AC over CD equals to CD times over CM. Again, AC over CD equals to CD over CM. Here we cross multiply this equation and we'll get that according to this equation, AC times CM equals to CD times CD. The value of AC is capital R minus 2R times CM. CM here it is equal to capital R plus 2R, and it is equal to CD times CD. CD equals to 8 units according to what is given as the equation, therefore CD times CD is 8 times 8. So in conclusion, we found out that according to rule number 11, R minus 2R times R plus 2R equals to 8 times 8. According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, when you get that R minus R times R plus 2R equals to R squared minus 4R squared, and it is equal to 8 times 8, that is 64. So actually found out that capital R squared minus 4R squared equals to 64. Okay. And what is the area of the green shape? Repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. Repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. Okay, so it is equal to the area of the quarter circle, that is the area of the circle over 4, that is to say it is equal to pi capital R squared over 4 minus the area of the small circle, that is pi R squared, and R is a small r. Again, the area of the green shape equals to pi times capital R squared over 4 minus pi R squared. Here we will take pi over 4 as a common factor out of those two expressions. So what is left from pi R squared over 4 after we took from it pi over 4 is a common factor? What is left is actually R squared and here it is minus 4r squared, because of the fact that minus 4r squared times pi over 4 equals exactly to minus pi r squared. So we found out that the area of the green shape equals to pi over 4 times capital R squared minus 4r squared. But we have already found out that capital R squared minus 4r squared equals to 64. Therefore, we can substitute capital R squared minus 4r squared by 64 here. So it will be equal to pi over 4, and this expression equals to 64. Here 64 over 4 is 16, so this expression in total equals to 16 pi. In terms of numbers, it is equal to 50.265 square units. Okay, we finished with the third method. In the next step, I will summarize the lecture. We'll start with the first method, of course. So I repeat on the question. We have here a quarter circle. Inside the quarter circle we have a small circle. We know that line segment CD equals to 8 units, angle ACD equals to 90 degrees. And our mission is to find out the value of the green area. Okay, so here we define the center of the circle here. We define the point of tendency of tangent CD with the small circle as point E. We define the point of tendency of tangent OP with the small circle as F. We join the center, actually we define the center of the small circle as point J. Then we join point J and F together by a straight line. Point J is the center of the small circle, point F is the point of the circle itself, therefore JF is the radius of the small circle that is equal to small r. And we have the radius that is drawn to the point of tendency, therefore according to rule number 1, this angle equals 90 degrees and this angle also equals 90 degrees. Likewise, join points J and E together by a straight line. Point J is the center of the small circle, point E is the point of the small circle itself, therefore J E is the radius of the small circle that is equal to R. And we have the radius JE that is drawn to the point of tendency, therefore this angle equals 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. This angle is equal to 90 degrees because of the fact that this is a quarter circle and point O is the center of the quarter circle. Okay. Here it is given as the equation that this angle equals to angle ACD equals to 90 degrees. AO is the radius of the quarter circle, therefore it is absolutely a straight line. So if we focus on this side of the straight line, AO is point C. Here the sum of the angles must be equal to 180 degrees according to rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side that is at this side of the straight line AO is point C, we have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO point C to 180 degrees. The missing angle must be equal to 90 degrees. Okay. Then from the center of the small circle, that is to say from point J, we draw perpendicular on CO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So inside quadrilateral JTOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the fourth angle. It must be equal in total to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this missing angle, the fourth angle, must be equal to 90 degrees in order to complete the sum of the angles in quadrilateral JTOF to 360 degrees. This angle must be equal to 90 degrees. Likewise, according to the same rule, in quadrilateral CETJ, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So actually, we found out that angle EJF, this angle, it is equal to 90 degrees plus 90 degrees is 180 degrees. And because of the fact that angle EJF is equal to 180 degrees, it means that line segment EGF is a straight line, because any angle that is equal to 90 degrees, it is defined as a straight line. And if line segment EGF is a straight line, it means that EF is also a straight line. So if EF is a straight line, it means that quadrilateral CEOF, this quadrilateral that has four right angles, it is a rectangle. Okay, quadrilateral CEOF, this quadrilateral, it is a rectangle. Why? Because it has 4 right angles. Here I repeat again. Quadrilateral CEOF is a rectangle because of the fact that it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side EF must be equal to side CO. EF equals to CO. But we already found out that EF equals to R plus R, that is 2R. Here, EF equals to 2R. And from this equation, 2R equals to EF equals to CO, we will derive that CO is also equals to 2R. Here, CO equals to 2R. Okay, we know that in any quarter circle, AO is the radius of the quarter circle. Okay, then we join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle that we defined as capital R. So OD equals to capital R. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, the square of the hypotenuse equal to the sum of the squares of the perpendiculars. That is to say, OD square equals to CO square plus CD square. Yeah, OD square equals to CO square plus CD square. So OD is capital R, therefore OD square is capital R square, and it is equal to CO square. CO is 2R, therefore CO square is 2R square. Plus CD square. CD is 8, so CD square is 8 squared, that is 64. So in conclusion, found out that according to equation number 1, R square equals to 2R square plus 64. That is to say, capital R square equals to 2R square is 4R square plus 64. We subtracted 4R square for this equation, equation number 1, and found out that according to equation number 1, R, capital R square minus 4R square equals to 64. Okay, then what is actually the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. And the area of this quarter circle is equal to the area of the circle, that is pi times capital R over 4 minus the area of the circle, that is pi R squared. Here we took pi over 4 as a common factor. Pi over 4 is a common factor. What is left from pi R squared over 4 after we took from it pi over 4 as a common factor? What is left is actually R squared. And here we took common factor pi over 4 from pi R squared. And here, what is left from pi R squared after we took from it pi over 4 is a common factor. What is left is actually minus 4 pi R squared. Why? Because minus 4 pi R squared times pi over 4 equals to exactly to minus pi R squared. So I found out that the area of the green shape equals to pi over 4 times capital R squared minus 4R squared. But we have already found out here that this expression capital R squared minus 4R squared equals to 64. According to this equation number 1. Therefore we can substitute capital R squared minus 4R squared by 64. We did it, and we got that here we substituted capital R squared minus 4R squared by 64, and found out that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of this green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first method. Then I presented to you the second method. Here we have only found out that CO equals to 2R in the first method. This is the radius of the small circle. This is also the radius of the small circle. And here we completed this quarter circle to a semicircle. We completed the quarter circle to a circle. And here we joined points O and L together by a straight line. Point O is the center of the circle, point L is the point of the circle itself, therefore OL is the radius of the circle, that is equal to capital R. Likewise, we joined points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is also the radius of the big circle, that is equal to capital R. Then we proved that here actually those two triangles are right triangles. Why those two triangles are right triangles? Because of the fact that it is given as the equation that this angle ACD equals to 90 degrees. AO is the radius of the quarter circle, it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have on this side of the straight line AO at point C? We have this angle that is equal to 90 degrees plus this missing angle. In total they must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. The missing angle must be also equal to 90 degrees. Here you actually extended the straight line BC by straight line. When you extend the straight line by straight line, the result that is DL must be also a straight line. So DL is a straight line. DL is a straight line. So if you focus on the lower side of the straight line DL at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. So this angle equals to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore this missing angle must be equal to 90 degrees in order to complete the sum of the angles on the lower side of the straight line DL at point C to 180 degrees. This angle must be also equal to 90 degrees. So we actually found out that triangle COD is a right triangle, and triangle LCO is also a right triangle. Then we proved that those two right triangles can go into each other. Why those two right triangles can go into each other? Because of the fact that here CO equals to CO, it is a common side that belongs to both triangles. CO equals to CO, and we have already found out that OD equals to OL. Why? Because they are both the radii of the big circle, therefore they are equal to each other. Again, LO equals to OD, they are both the radii of the big circle, therefore they are equal to each other. So we prove that the hypotenuse and one perpendicular and two right triangles can go into each other, therefore those two right triangles can go into each other. And I'll explain you why it is enough in order to prove that the two right triangles can go into each other. Why? Because if you have two right triangles here, triangle ABC and triangle EDF, and they have the same hypotenuse, both the hypotenuse plus they are equal, 1 to 5 units, and they have one side, both those two right triangles, and they are equal to 3 units. Therefore, the third side must be also equal to each other. Why? Because according to the Pythagoras theorem, the third side in both triangles equals to the square root of 5 square minus 3 square. 5 square is 25, minus 3 square is 9. That is 25 minus 9 is 16, and the square root of 16 is 4. So, found out that if we have hypotenuse and one perpendicular in two right triangles that are congruent, then the third side must be also congruent. Okay? You can see here, the third side in both those two right triangles is equal to 4 units. That is the reason that is enough to prove that the hypotenuse and one perpendicular in two right triangles can go into each other, and therefore those two right triangles will can go into each other. So we actually found out that those two right triangles can go into each other, and from the fact that those two right triangles can go into each other, we will derive that CD equals to CL. CD equals to CL or LC, according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding sides, that is to say CD and LC, also must be equal to each other. But it is given us the equation that CD equals to 8 units, or CD equals to 8 units. And for this equation, 8 equals to CD equals to LC, we will derive that LC is also equals to 8 units. LC is also equals to 8 units, LC equals to 8 units. Okay? Then I presented to you rule number 11, and we implemented rule number 11 in our drawing. Okay? I repeat again that we extended the radius AO by straight line until it intersects with the circle at point M, and we extended here the straight line DC by straight line until it intersects with the circle at point L. So here rule number 11. According to rule number 11, if we have chord AB that intersects with chord CD at point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing, right? Because in our drawing we have chord AM, this is chord AM that intersects with chord LD at point C. Again, chord AM intersects with chord LD at point C. Again, chord AM intersects with chord LD at point C. Therefore, we get that according to rule number 11, LC times CD equals to AC times CM. Again, LC times CD equals to AC times CM. Again, according to rule number 11, we get that LC times CD equals to AC times CM. LC equals to 8, CD equals to 8, AC equals to capital R minus 2R, and CM equals to capital R plus 2R. So in conclusion, we found out that 8 times 8 times capital R minus 2R times capital R plus 2R. So 8 times 8 equals to capital R minus 2R times capital R plus 2R. 8 times 8 is 64, and capital R minus 2R times capital R plus 2R equals to the, according to the algebraic identity, that A plus B times A minus B equals to A squared minus B squared. Here A equals to R and B equals to 2R. Therefore A squared will be equal to A equals to capital R squared. Yes, therefore A squared is capital R squared, and B equals to 2R, therefore B squared is 2R squared. Okay, so if we're going to find out that 64 equals to capital R squared minus 4R squared. Okay. And what is the value of the green area? The value of the green area equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The value of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi r squared over 4, that is the area of the circle over 4, minus the area of the small circle, that is pi r squared. Here we took pi over 4 as a common factor of those two expressions. So here pi over 4 is a common factor. What is left from pi r capital R square over 4 after we transform pi over 4 as a common factor? What is left is actually capital R squared. And what is left from minus pi r squared after we took from it pi over 4 as a common factor? What is left is actually minus 4r squared. Why? Because minus 4r squared times pi over 4 equals to exactly to minus pi r squared. Okay, but here we have already found out that this expression capital R squared minus 4r squared equals to 64. Therefore we can substitute capital R squared minus 4r squared by 64. We did it and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we actually found out that the area of this green shape equals to either 16 pi squared, or in terms of numbers it is equal to 50.265 square units. Okay, so we finished with the second method. In the next step, I'll present to you the third method. We already found out that in the first method that CO equals to 2R. This is the radius of the small circle. This is also the radius of the small circle. And here it is given as the equation that this angle equals to 90 degrees, therefore this angle must be also equal to 90 degrees, according to rule number 3. Then we actually completed this quarter circle to a semicircle, and then we joined points D and M together by a straight line. We joined points A and D together by a straight line. In this way, we created peripheral angle ADM. And then we extended the radius AO by a straight line. So, and here point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle that is equal to capital R. When we extended AO, that is a straight line by straight line, the result is AM, that is also a straight line. So we have AM, that is a straight line that passes through the center of the semicircle, and it is equal to 2R. R plus R is 2R. So any chord that is equal to 2R and passes through the center of the semicircle must be the diameter of the semicircle. Therefore, AM that is equal to 2R must be the diameter of this semicircle. So AM is the diameter of this semicircle. And we have peripheral angle ADM that rests on the diameter of the semicircle, that is AM. And here we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. Here the diameter of this circle is AB, and we have the peripheral angle AMB that is rest of the diameter of the circle, that is AM. Therefore, peripheral angle AMB must be equal to 90 degrees according to this rule, rule number 5. Actually, we can implement rule number 5 in our drawing, because we have peripheral angle APM that rests on AM, that is the diameter of this circle. Therefore, this angle and peripheral angle PM that rests on the diameter of this circle, peripheral angle ADM that rests on the diameter of the circle must be equal to 90 degrees according to rule number 5. Then we define angle DAMA as alpha, and we define angle DAM as beta. Then we focus on the right triangle, triangle ADM. On the right triangle, triangle ADM, this is the right angle, it is equal to 90 degrees. So if this angle equals to 90 degrees, it means that the other two angles must be also equal to 90 degrees, because 90 degrees plus 90 degrees is 180 degrees, that is the sum of the angles in any triangle. That is to say, alpha plus beta in total must be equal to 90 degrees in this right triangle, triangle ADM. If alpha plus beta equals to 90 degrees, it means that alpha equals to 90 degrees minus beta. Then we subtracted alpha from this equation and found out that beta is also equals to 90 degrees minus alpha. Then we focused on the right triangle, triangle ACD. In this right triangle ACD, this angle equals to 90 degrees. This angle equals to beta. Therefore, the missing angle must be equal to 90 degrees minus beta. But here we have already found out that 90 degrees minus beta equals to alpha, so we can substitute 90 degrees minus beta here by alpha. Likewise, in the right triangle, triangle DMC, this angle equals to 90 degrees. This angle equals to alpha, therefore the missing angle must be equal to 90 degrees minus alpha. but 90 degrees minus alpha equals to beta, according to this equation. So we can substitute 90 degrees minus alpha by beta. Then we proved that those two right triangles are similar to each other. That is to say, triangle ACD is similar to the right triangle, triangle CDM. Okay, so why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. Okay, in addition, those two angles they are both equal to beta, therefore they are equal to each other. And finally, those two angles they are both equal to 90 degrees, therefore they are equal to each other. So we prove that those two triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that AC over CD equals to CD over CM. Again, AC over CD equals to CD over CM. AC over CD equals to CD over CM. So here, suppose multiply this equation, we found out that AC times CM equals to CD times CD. What is the value of AC? AC equals to capital R minus 2R. So substitute AC by capital R minus 2R. What is the value of CM? CM equals to 2R plus capital R. So substitute CM by 2R plus capital R. And it is equal to CD times CD. CD equals to 8, so CD times CD is 8 squared, that is 64. So in conclusion, we found out that R minus 2R times R plus 2R equals to 8 times 8. 8 times 8 is 64, and R minus 2R times R plus 2R equals to R squared minus 4R squared. So in conclusion, we found out that R squared minus 4R squared equals to 64. And you know that the green area equals to the area of the quarter circle minus the area of the small circle. Again, the green area equals to the area of the quarter circle minus the area of the small circle. That is to say, the green area equals to the area of the quarter circle, that is pi r squared over 4, minus the area of the small circle, that is pi r squared. Here we took pi over 4 as a common factor out of these two expressions. So pi over 4 is a common factor. What is left from this equation, from pi r squared over 4, after we took from it pi over 4 as a common factor, what is left is actually r squared. And what is left from minus pi r squared after we took from it pi over 4 as a common factor, what is left is actually minus 4r squared, because minus 4r squared times pi over 4 equals to exactly to minus pi r squared. But we have only found out that the expression r squared minus 4r squared equals to 64, therefore we can substitute r squared minus 4r squared by 64. We did it. And we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total this expression equals to 16 pi. So we found out that the area of this green shape equals to either 16 pi, or in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.